Problem 2 says a loaded elevator car with a mass of 1,000 kilograms is moving downwards at 5 meters per second. The elevator is hanging from a steel cable under tension. The elevator smoothly comes to a stop after 5 seconds, assuming constant deceleration. So the first question is part A, and this says draw and label a free body diagram of the elevator. Explain in words what direction the elevator is accelerating. So I want to talk about some of the answers that I saw, which had the elevator here, labeled the mass, 1,000 kilograms, and then drew the initial velocity, which is 5 meters per second. You might have even drawn the steel cable here that's holding the elevator up. So diagrams like this can be helpful for understanding the problem. They can be helpful for sorting out our initial information, figuring out where it goes. But this is not a free body diagram. So an FBD is a particular type of diagram that shows all of the forces acting on the center of mass. So we usually just represent the center of mass as a dot. You can draw the elevator around it if you want. But all we need is the dot, and we need arrows that show the forces. So we've got our tension force pulling up, and our other force has to be the weight, and that has to be going down. Because our elevator has mass, gravity acts on all massive objects, so we have a weight pulling down, and we're given the fact that there's a steel cable holding it up, which supplies the tension. So this diagram is not what we're looking for. We're looking for a free body diagram, or FBD, like this one. So next we're told to find which direction the acceleration is going. So we're starting with a downward velocity, or a negative velocity, and we end at rest. V final equals 0 meters per second. So our acceleration starts down and ends at 0, which means our acceleration vector is pointing up. We are accelerating upwards. So that does it for part A. We can go to part B now. It says to find the magnitude of the elevator's acceleration as it comes to a stop. So find the magnitude of A, and I'll represent magnitude with these vertical lines. So we're given delta t, we're given v0, we're given v final, and we need to find A. So we can look at our list of 1D kinematical equations and find an equation that satisfies the property of having all of these numbers in it. So the equation that does that is v final equals to v initial plus A times delta t. So we can just go ahead and plug our numbers in. V final is equal to 0. V initial is negative 5.0, and you'll see why the negative matters in a second, plus A times 5.0 seconds. So I want to rearrange this equation so A is by itself, so I'm going to add the 5 meters per second to both sides. And I end up with 5 is equal to A times 5. Then I would divide both sides by that 5 seconds, and I end up with A is equal to plus 1.00 meters per second squared. So you can see if I had gotten the sign wrong on this v0, if I hadn't recognized that the v was pointing down and therefore it was a negative quantity, then I would have gotten a negative acceleration. But because I put all of my quantities in with consistent signs and consistent directions, my A comes out positive, which is what we described before in our diagram. We're accelerating upward, so A is positive. We're asked to find the magnitude of A, but since A is already positive, this is the same number. 1 meter per second squared. So we're ready to go to part C. Part C asks us to find the weight of the elevator. So this is fairly straightforward. We just have our equation for weight. Weight is equal to mass times g, the acceleration due to gravity, which is 1,000 kilograms times 9.8 meters per second squared. And you can do this multiplication and it comes out to 9,800 newtons. Part D says find the tension on the steel cable. So we labeled this as capital T. I'll redraw our FBD again here. We have T going up and we have W going down. So to find T, we need to use Newton's equation F net equals m times A. Now the way that we find F net, we always go back to our diagram and we label the forces here and we recognize which ones are pointing up and which ones are pointing down, and we construct our equation that way. So we've got a positive T and a negative W. T is going up, W is going down. This is our net force, and it's equal to ma. If we want to find T, we're going to add W to both sides so that T will be by itself. And now we're ready to plug in numbers. T is equal to 1,000 kilograms times A is what we found in part B, 1.0 meters per second squared. This is from the previous section. And then W, we already found here, it's 9,800 newtons. So we're really just plugging in the work that we did in parts B and C leading up to this. Now if we plug these numbers into our calculator or just do the multiplication and addition, we end up with 10,800 newtons. This is our tension. And we can check that these numbers make sense. So T, 10,800 newtons, weight is 9,800 newtons going down. So we expect from this our net force is going up. If our net force is going up, the acceleration has to be going up in the same direction. And this is consistent with what we decided earlier in parts A and B, that acceleration is going up. So these all seem like reasonable numbers, and the answers check out for us. Problem 3 covers two-dimensional kinematics. It says you kick a ball at an angle theta equals 30 degrees above the ground with an initial velocity of v0 equals 10 meters per second. It then hits the ground 8.84 meters away. So part A just says to draw and label a sketch of the situation. So the situation is just you and the ball. The ball has been kicked with an initial velocity. v0 equals 10.0 meters per second. And then it lands somewhere way over here. 8.84 meters away. So this is our delta x. Now, where a few people ran into trouble was understanding where the right triangle comes. So the right triangle is where we drop this vertical line from our v0, and we use that to find v0x and v0y if needed. So that leads us right into part B, which says find the initial velocity in the x direction, v0x. So if you hadn't drawn your right triangle in the diagram yet, this would be a good time to draw it. Here's our right angle here. Here's the angle theta. And since that's getting kind of crowded, I'll redraw the angle theta as well as the rest of our right triangle. So the hypotenuse of the triangle is 10 meters per second. The opposite angle is v0y, and the adjacent angle is v0x. Now if we look at our trigonometry identities, the sine of theta is equal to opposite over hypotenuse, so that would give us v0y. That's not what we want here. But the cosine of theta would give adjacent over hypotenuse, or v0x, over 10.0 meters per second. So if we rearrange this by multiplying both sides by 10 meters per second, then we get that v0x is equal to 10.0 times cosine of 30 degrees. And this is in meters per second. I plug that into my calculator, then the value I get here is 10.0 times 0.866. So my velocity ends up being 8.66 meters per second in the x direction. And so we can check that with our triangle inequality. We've got 8.66 meters per second, and that is less than the total initial velocity because we're talking about just the component in one direction. So we'll go on now to part C. So part C says how long does it take for the ball to hit the ground, which is asking us to find delta t. So there are a couple ways we could do this. We could look at things in the y direction, use our delta y equation, or we could use our delta x. Now both of these could relate our information about y or x to delta t, but we already know a lot more about delta x because we know v0x and we know that the acceleration in the x direction is equal to 0. So x turns out to be a much simpler way to go here. Y is certainly possible, but it will involve more math. So I'm going to write delta x is equal to v0x times delta t plus 1/2 a times delta t squared. So the next observation I need to make is that our acceleration in the x direction is equal to 0, which means this whole term here goes away, and I'm just left with delta x is equal to v0x times delta t. And if I rearrange this by dividing both sides by v0x, then I end up with delta t is equal to delta x over v0x. So we have our delta x from the problem, 8.84 meters. And our v0x comes from the previous part, which is 8.66 meters per second. So the meters cancel, and this is inverse seconds, so we end up with seconds on the top, so our units are okay. And if I plug this into the calculator, 8.84 divided by 8.66, I end up with 1.02 seconds. So now if I move on to part D. So part D gives us a lot of information. It says that just before hitting the ground, the velocity in the y direction, vfy, is 5 meters per second downward. So I'm going to write minus 5.00 meters per second. Because we're working in a coordinate system where up is positive and down is negative. So it asked us to find v final, the magnitude of the ball's final velocity just as it hits the ground. So what I need to recognize here is that as the ball hits the ground, it's coming in with some final velocity which has components in the x and y direction. So I have v final x and I have v final y. So we're given v final y, so the missing component here is v final x. But if I recognize from the previous part that our acceleration in the x direction is equal to 0, that's equivalent to saying that the velocity never changes. V final x is equal to v initial x. And that is still equal to 8.66 meters per second. We have v final y is equal to 5 meters per second. So if I use my Pythagorean theorem on this triangle here, then I can write down that v final squared is equal to 8.66 squared plus negative 5.00 squared, and the units here, meters per second squared. So if I put this in my calculator, what I end up with is about 100 meters per second squared. And then I need to take the square root of both sides, which will give me v final is equal to 10.0 meters per second.